pretty good. All right, so this is what I was trying to say. So we're going to prove that given any real number, this limit does not exist. Okay? So again, maybe the picture is helpful. Here's C, right? We know that the graph is +1 on all the rationals and -1 on all the irrationals. So does anybody have a suggestion? How do I mean, just in general, this is something important for the test. How do you prove that limits of functions don't exist? What's our standard go-to method? Sequences, using sequences, exactly. What we need is a sequence of points that converges to C, but then that the image of that sequence does not converge, or if we need two sequences converging to two different things, that would be fine as well. Okay, so can somebody tell me how I'm going to get a sequence that converges to C that I can work with? Can I borrow your book real fast? Oh, that's not too good. Does anybody have the text?
Yeah, we have it.
Okay. Just borrow it. I got it. Okay, so going back, I'm going to try and find the right place here. It might be in this section, actually. So there's a result about this, isn't there?
Yeah, I think.
Is it proposition 4.6?
That's what I'm going to use, but no, I'm looking for something about sequences of rational numbers. It's so hard because the text is pretty dense. To find the right result here. Yeah, I thought it would be in chapter 3. I'm not finding it. There's a theorem that says that given any real number, you can create a sequence of rationals that convert. It's 3.5. I just opened to it now. Theorem 3.5, right? So by theorem 3.5, there exists a sequence xn, which is values that are in Q, with xn converging to C, right? So we know that. We actually did this in class. This was one of the results in class. So we have that sequence. So now we have that, but if we look at the image of the sequence, f of xn, so this is f of a bunch of rational numbers, right? So actually this is a sequence of 1, 1, 1, 1, 1, 1, and so on. So of course it converges to 1, right? Since f of xn equals 1 for all natural numbers n. That make sense?
Yes.
Okay, so we have that. So far, is that a contradiction so far? No, there's no contradiction there so far. I'm going to have to do something else.
Yeah.
Because this could be the L, right? This could be the limit or the limit point of the right, the limit of f of x, maybe it equals 1. So far there would not be a contradiction. So what else do I need to do right now?
So we're going to do the same thing. There exists.
Right. We need to do another sequence, don't we? Okay, so similarly there, and this is also theorem 3.5, there exists a sequence yn in the irrationals, r minus q, with yn still converging to C. So you're on the input side of things, you're still just letting y sub n converge to C. However, the sequence f of yn would just be the sequence -1, -1, -1, -1, and that's just a constant sequence -1, since f of yn is equal to -1 for all n. So for every natural number, that would be the case. Okay, so now you have two different values here, so therefore this limit does not exist. So I'll just put that over here. Okay, thus the limit of f of x as x approaches C does not exist. Right. Does not exist. Pretty happy with that? Make good sense? Thank you so much. Okay. Great. So we did that one. Okay. What else am I going to do here? Oh, okay. I've got another one here while we're talking about this stuff. Let's go on to number 4. Okay, I'm probably not going to give you like true-false items on the test, but for now I'm going to do that because it's just kind of helpful for asking some good questions here. So this is true or false. Okay, so here it is. Let f and g be functions from R to R, and let c be in R. Okay, so then if the limit of f of x as x approaches c and the limit as x approaches c of f of x times g of x, if both of those limits exist, so these both exist, if these both exist, then is it true that the limit of g of x as x approaches c exists? So I'll let you think about it for a minute while I erase the rest of the board here. So the limit of f of x exists, and the limit of f of x times g of x exists. The question is, does that mean that the limit of g of x exists?
I think true.
Think true. We have one vote for true so far.
My gut says false, but
Oh, we have a vote for false.
I think it's
False?
I think it's false, but
You know, you kind of feel like you want to like use the limit theorems, right? And it's sort of
Yeah.
like if two limits exist, then you can combine them, right? We have like I could choose to add these two, right? So if these both exist, then the limit of f of x plus f of x g of x would also exist, right?
yeah.
So plus minus, we can do multiplication of this, right?
Yeah.
So the limit of f of x times g of x would also exist, right? So for this one, we actually have to take these two and do division, right? So here would be my question then. Is it true that the limit of g of x, is it valid to write that as this over
Yeah.
this?
I think it's true.
That's okay?
That's probably true.
So if this exists and this exists, then and if this is a real number and this is a real number, you form the fraction, and that would be the answer here. Are people changing their votes?
I think so, but I wasn't sure to begin with.
Okay.
Isn't
How come it's
it,
not like
isn't it
this?
provided that c is not equal to 0 though for...
No, the limit. Like as long as the
You're on the right track. You're on the right track. If this denominator is 0, then I don't care that this exists and this exists. You can't divide it and get an answer, right? So this was the right intuition, right? If this had said, if the limit of f of x exists and is not 0,
Yeah.
then this would have been correct. Okay, so it's a little tricky. This is why I say I'm not going to do this kind of question on the exam like this, because it's a little tricky. If this limit is not 0, then we would be okay. But as it is, this is only true if the limit of f of x as x approaches c is not 0. So it has to exist and be non-zero. Okay.
So if it's given that it exists, we can't say that it doesn't equal to 0? Unless it's given?
Right. 0 exists.
Oh.
Right. 0 is a real number. If this limit is 0, it exists. There's nothing wrong with that. So now what I have to have, though, is a counterexample. It's for a false statement.
That's
So
what I was trying to think of.
yeah, so we've got to think about a function that we could use here. It would be like a nice counterexample. So, so we need to have one function. Well, we need to pick a value of c, first of all. What would be a choice for c that we could just make up? Because we can kind of choose whatever we want for c. Let's just make it 0. Let's make it 0. Let's make it right at 0. That would be the best choice. That's, I think, the best choice. Okay, so we have that. And I want to make a function. So can somebody give me a function right here? So the limit of the function as x goes to 0 is 0.
1
X.
over x.
No, 1 over x would blow up.
Just
Oh,
use
okay.
x and then for
Have you seen my solutions yet?
no.
Oh, okay.
But if we use
That's exactly
if
right.
we use x and then we use g of x as 1 over x when we're multiplying the x's, but g of
Okay,
x
so we use that one, and then we're going to let, okay, so this is my f of x. Perfect, right? That works, right? That limit is 0. And then let's make g of x. What do you want to make g of x?
1 over x.
Okay, now be careful. G has to be a function from R to R. So
Oh.
every single real number has to have a value. I will let you
1
use
over
that.
x,
I will let you use that, but you can only use that for the non-zero
and
x's.
then just pick endpoint like 1 for x.
If x equals 0?
Yeah.
Of course, since we're taking limit as x approaches 0, we don't really care what the value is at 0. So you can pick any number you want here. Okay, so perfectly fine like that. Okay, so then if we look at this, so this is f and this is g. So then what is f of x, g of x? So f of x, g of x equals, well, as long as x does not equal 0, you're multiplying these two together and you're going to get 1 if x does not equal 0. And when x is equal to 0, you're going to have 0 times 1, which is 0, right? So actually this would be the function. Okay, and then you just simply note that the limit of f of x, g of x, as x approaches 0, that limit is equal to, so as x approaches 0, we're not looking at what happens at 0. The only thing we see is that the value of the function is 1. Okay, so this is a 1. That exists. This limit is 0. That exists. And now the problem, though, is that this limit right here does not exist. The limit of g of x as x approaches 0 does not exist. And you can just say by class, because we did that one in class, right? We showed it in class that doesn't exist. So that's a really, really good. If you forgot to piecewise define it and you just said g of x equals 1 over x, I'd probably give you almost full credit, maybe full credit. I might take off at most 1 point. Depends on how many points it was worth. It would not be a big mistake. Okay, so that's kind of the idea. Make f and g basically cancel out to a constant. Make f a really nice function whose limit does exist, and then the g is the reciprocal of that, essentially, that does not exist. People feel okay? These are the kind of examples, you know, you see the spirit of these questions. Some of them are just proofs. Some of them are giving an example of something. Don't give up on the problem. Like if you have part of an idea but you don't quite see the whole way through, still write down what you know, because I might give you some credit for at least setting this up more or less correctly, even if you don't quite have the right functions at the end of the day. It's still very, very useful to do that. Okay, everybody good on that example? Okay, let's go on to something else. Okay, here's another one. This is also true, false. True or false? A bounded infinite subset of Q. If we take a bounded infinite subset of Q, is it true that it must have an accumulation point in Q? So we have a bounded infinite subset of Q. Must it have an accumulation point in Q? I'm going to start by reminding you the definition of an accumulation point, because I always think that's good to review. Okay, so X is an element of the real numbers, is an accumulation point of some set A if, for all epsilon greater than 0, if we take the neighborhood x minus epsilon to x plus epsilon, and we subtract x from that, so if we take x out of that neighborhood, it's like a punctured interval. You take out that one single point. If it's an accumulation point, then the intersection of that with A should always be non-empty. A non-empty intersection. That's the definition. That's the definition. Okay, that's the definition. Okay, so again, here's X. You take any neighborhood of it, right? Then there has to be some point, at least one point of A somewhere in there other than just X itself. If X is an element of A, that doesn't make it an accumulation point. If it's isolated, if there's no other points of A other than just X itself, then it would be isolated. Right, so this is an accumulation point. So here we want to know, can we make a bounded infinite subset of Q? See, if it didn't need to be bounded, it would be easy to see that it's false, because one example of an infinite subset of Q would just be all of the integers. That's an infinite subset of Q, and those would all be isolated. So if it just said an infinite subset of Q must have an accumulation point in Q, that would be false. Now, but we're not, of course the integers is not bounded, so now we're saying, well, what if it's bounded? Can we make a bounded infinite subset of Q such that every single one of its points is like isolated? Everything is an isolated point. Or that the only accumulation point is something that's irrational. Could we make this subset of Q such that the accumulation points, if there are any, are irrational? See, how can we make accumulation points? How do they arise? If I take a whole interval, then of course the whole interval is accumulation points, and the endpoints get closed up, right? The accumulation points of the open interval 0, 1 would be the closed interval 0, 1. That's fine, but the problem with taking intervals now is you're going to get irrational numbers in those intervals. We can't work with intervals here, right? If we do that, then it's not going to be a subset of Q. So how else could a set look? If it's not an interval, it's not like a whole interval of points, how else can you make sets inside of the real numbers? So the integers is an example. The integers is not an interval. It's just a bunch of points, right? That's what I'm looking for. Sequences. Yeah, think about sequences for a minute. So if you take a sequence, of course some sequences might be unbounded, but think about bounded sequences.
Between 0 and 1, we can do 1 over n, right?
1, 1/2, 1/3, 1/4. So let's think about this example. 1, 1/2, 1/3, 1/4, 1/5. There's that set, right? That is a bounded infinite subset of Q. Now, what do we know about the accumulation point or points of that?
0.
Right, has 0 as accumulation point. Okay, so that would not be a counterexample, because This is a bounded infinite subset of Q, and yes, it has an accumulation point in Q because Q is rational. Okay, so do you think that will always be true? So anytime you have a convergent sequence, you'll have one limit point, which is always the limit of the sequence. Sometimes these accumulation points are called cluster points or limit points. They would be the limit of the sequence. So if we were going to give a counterexample, what about using a sequence that converges to an irrational number but consists of rational numbers? Like our set has to be a subset of Q, but we need to end up with an irrational.
We can do a radical 2, right?
Okay,
There was
so how's your sequence going to look?
There was an example in the book. It was like 1 over...
Right, you guys are on the right track. This is false. Okay, so here's a counterexample. Okay, square root of 2, you want to use that as your limit point? What you would need to do, so let's think about the square root of 2 for a second. What is the, does anybody know the decimal expansion of that? It's like 1.4...
1-4 something.
something.
I think those are.
Okay.
I think those are the first.
Those are the first 3. I don't even know. Does your calculators, do your phones do this?
Yeah, it should,
Probably.
I don't even know.
it should
I don't know if
be-
my phone is very good or not. Think you can find it on there?
I think so. Hang on.
Okay. 1.414.
1.414, How far you want to go?
That's good enough.
Okay.
That's good enough. Great. Thanks. Okay, good. So basically what you can do, guys, is you can create a sequence by just using the first so many decimals of it, right? So this is, I think, what you're thinking of from the book, right?
Yeah.
Right, so
Yeah.
each one of these is rational. Each one of these is rational because each one of them is a terminating decimal. So these are all rational numbers here. 1.414, right? Next one is 1.4142, and so on. That is a sequence of rationals, right? It's bounded, okay? So xn, notice it's always at least 1, and it's going to be at most 2, for example. So this is bounded. And each xn is in Q. Remember, when you're explaining your answer, make sure you address everything. It's bounded, it's obviously infinite, it's a subset of Q. It's a sequence, and the only accumulation point is the square root of 2, which is not in Q. A sequence, a convergent sequence can only have one accumulation point. That's the most it can have. It cannot have more than that.
Sorry.
Okay? Is everybody comfortable on that?
So, sorry. So you say convergent sequence can only have one accumulation point, which is just the limit.
Which is just the limit of it. Yeah. Yeah, that's exactly right. Does that make sense? Well, actually, let's actually do that as our next example. Let's actually prove that. Let's prove that a sequence can only have one accumulation point, a convergent sequence. Okay? So this is number 6. Let's try to prove that one as well. We're going to finish early, guys, for sure. We're doing really well here, plus my foot's telling me I'm going to have to stop early. But we'll keep going here a little bit longer. But suppose that xn converges to x. Prove that if y does not equal x, then y is not an accumulation point of the sequence xn. Try and do that. So the only accumulation point could be x. Okay, let's try to prove this one here. Okay. So you have, maybe just for a picture here, you have xn like converging like this. x1, x2. We'll just kind of imagine this kind of a picture. So your x is over here somewhere, right? Suppose that you have some other number over here, y, which is not the same as x. Okay. And the idea is that it's not an accumulation point. So I've erased the definition. Maybe I need to put that back up again. Y is an accumulation point if and only if for all epsilon greater than 0, the neighborhood y minus epsilon to y plus epsilon minus y, right? We intersect that with, this accumulation point of A. If we intersect that with A, it's not empty. Okay. This is the definition. So what we need to do then is we need to figure out how to make a neighborhood. So the negation of this, right? If I want to negate the definition of accumulation point, then instead of for all epsilon, we're going to say there exists a bad epsilon. There exists an epsilon such that this intersection is empty. Looking at the picture, you think you could make a neighborhood around y so that the intersection of that neighborhood with the set A in this case is this is A right now, right? Could you make a neighborhood around this point in such a way that it would have nothing, that neighborhood would have no common points with the sequence?
So we're going to choose epsilon to be the minimum.
So that we definitely want to do this. We want to find an epsilon that we can choose. Let's figure out what it should be.
It will be the minimum of y minus x.
So when I take minimum, I'm always taking minimum of multiple things.